Awesome. Um, right. So, hello. My name's Tom Miller. I'm studying an MSc in predictive modeling and scientific computing at Warwick, and my supervisor is Rebecca Nealon. Um, my project is called Machine Learning on the Hunt for Misaligned Planets. So, misaligned planets are planets that are inclined in orbit relative to the spin of the star that they're orbiting. We see existence and observations of misaligned and warped planets forming disks or protoplanetary disks in reality, and there is also a theoretical justification for the existence of misaligned planets. So there's good reason to be studying them. And now looking at, I guess, coplanar planets and what's used on them for sort of mass measurement and other stuff. Yeah, we can see from the figure on the right. The gravitational influence of a planet can be determined by its kind of influence on the velocity profile of the disk around it. This has been done by Pant in 2018, looking at effectively the white line being the line you'd expect this velocity profile to follow through Keplerian velocity, and the white being what we determined the effect of this planet has had on that, and that's corresponded to a deviation of 12%. But this can then be used this deviation can be used to determine what we then anticipate the mass of that planet to then be. And so this was then done on a range of planets in 2020 from the ALMA dataset, and this fit relatively well. But there was one planet that's like anomalous and it didn't quite fit the pattern. And in 2023, Kanagawa paper basically looked at the reason for this and used form matching using a kind of a range of different studies to determine that this is potentially a misaligned planet based on the dust continuum profile being sort of diminished compared to what you'd expect from a coplanar planet, and maybe the channel map signature, this kink that we see, being slightly more pronounced in different ways than you might expect from a coplanar planet. But this is all kind of form matching. Can we sort of bring some computational, I guess, like algorithm approach to the tool? So machine learning's been used in astrophysics quite a lot, particularly neural networks. They've been used in the past to detect planets based on images and predict the mass of a planet from basically images or just the data from the disk itself. What about if this approach could kind of be extended to determining if a planet is misaligned or coplanar? And if that is the case, if you can determine a planet is coplanar or misaligned, can you then predict its inclination off of that? So some of the work that I've done in the past being my undergraduate project on this as well. I'm still in the process of doing my MSc project, so the results aren't complete, but I'll sort through where I've got to with looking into this now. So using the surface density profile, you can effectively observe the impact that a planet has on the disk. So the size of the kind of crater it creates within this profile. You can see the dotted line being like the undisturbed profile if there wasn't a planet in there that you would expect, and the blue line being basically what you do then see in this disk, and the size of this can then be used to determine, well, effectively how big and how massive this planet is likely to be. And from this figure here, you can see that an inclined planet on the bottom panel is of the same mass, but shows a far reduced influence on that disk, which is interesting and would like to be, I guess, quantified. So using some empirical formulas, you can effectively determine a prediction on the masses. And as you look, I guess, here you can see the 1, 2, and 5 Jupiter mass planets. Whilst the predictions aren't perfect for the non inclined or the coplanar case, they give relatively reasonable approximations of these in this case. And so you see for all 3 of the different mass cases that as you increase the inclination, you effectively end up with a reduced mass estimate, and quite significantly so by the time you get to 20 degrees. So if you're predicting the mass of a planet based on its surface density profile and it was misaligned, you're likely to be getting it like substantially wrong potentially. So that's all well and good. How does that affect the velocity structures? So is there anything we'd expect to see there? So looking at synthetic sort of velocity observations, we can see the plot on the left is a difference in Keplerian velocity of the gas in a disk, um, and centered around the planet being about 225 AU on the x-axis there. And you can see before and after this planet, it's got kind of this uniform symmetric deviation from Keplerian velocity that you'd expect to see. And the key here being it's kind of pronounced and it's symmetric. If you look at a planet that's inclined at the same kind of rough Z point, so along the midplane, you see a kind of similar profile but far less pronounced. So similarly symmetric, but far less obvious that the planet is there at 20 degrees, following on sort of similar to what we saw in the surface density profile. But then if you look at the case where it's the z-axis is fairly large in magnitude, so it's away from the midplane now, so outside of the kind of the central area and in the disk, you see a very asymmetric plot in itself. So it ends up sort of, I guess, yielding some really quite interesting results, and I guess cast some doubt onto whether or not if you were to apply coplanar techniques to misaligned planets, are you going to yield kind of accurate results? And maybe not. So the looking at now channel maps and trying to quantify the mass, like I've talked about before, you can see the difference in the way that this kink exhibits in a coplanar and a misaligned planet. In the channel maps here, in the coplanar planet on the left-hand side, you see that whilst the shift is quite isn't actually as pronounced, it's quite large in the actual overall structure of the disk where I circled there. But actually, what you see is this ends up causing a larger deviation, so a larger perceived mass than what you see with this this 20-degree case. But actually, the kind of overall, I guess, influence, the kind of the change that you see is a lot more localized. It's a lot more kind of one bump, but very a lot less effect on the overall disk structure itself when it seems to be misaligned. And so you might be getting kind of a misrepresentation if you were to use this approach on misaligned planets. So looking at now the same plot before with surface density, but now with channel maps on, you see similar kind of relatively accurate, like not completely perfect for 1, 2, and 5 mass for coplanar, and then just like a really consistent decrease across the board as you increase the inclination on the perceived mass that you get. So consistent results with the surface density profile. So what now? The work I'm currently doing as I sort of progressing through the dissertation stage of my master's is I'm running simulations using Latin hyperQ sampling on kind of the similar types of things, but on more data, so that I can potentially use it for machine learning techniques. And using Latin hyperQ sampling for the most efficient sort of spread of all the parameters. I am automating like the sort of traditional mass predictions, trying to get the stuff that I've just shown you to be run automated, and so I can use that and take it a step further, looking into misaligned planets. And then I'm also currently looking to create a residual profile in the channel maps, basically looking at, now that we're not just studying, I guess, the size of the kink, we're also looking at the shape potentially. If it's a more localized kink, it makes sense to look at the deviation, like I did with the synthetic velocity observations, and look at the, I guess, the residual profile of the channel maps as opposed to just the profile. So you can use that. And then how I'm intending to use that in the future is to classify the planet as misaligned or coplanar, basically looking at whether or not like there's something I can use in like the shape, if I can use computer vision algorithms to predict whether or not this is going to be the case or not. And then following on from that, if that's possible, like I mentioned before, predicting then a kind of corrected, like an aligned mass and inclination estimate from these. I guess the idea that it might be coplanar or it might be misaligned, and then give a correct mass and inclination estimate. And then finally, using all of this, I can then sort of quantify the extent of error that, so say you were to use sort of traditional coplanar techniques on a particularly misaligned planet, how far wrong would you be going? And that's sort of where I'm aiming to get to. Thank you guys for listening. If there's any questions, I'm happy to take anything.
Thank you very much for the exciting talk. I was wondering about, so if the inclination is quite high, then the planet at some point will sort of leave the disk and then plunges back in. And so you'd
Yeah.
actually expect a signal in the scattered light, or even if not, if the inclination is not that high, you'd expect a signal in the optically thick lines more so than the optically thin lines because they probe closer to the surface. Are these things that you're worried about, or the machine learning would pick up on?
That's actually not something I've particularly looked into. But yeah, I mean that sounds like something that I have to think about. Um, so how do you think that would, like, I guess, manifest if in my predictions, you say?
I think it's something that you might want to look at as a smoking gun to identify some of these systems where the other evidence that there might be an inclined path because um, like you don't expect the signal in the optically thick lines more so than the optically thin lines. And so if there are some systems that have a stronger kick in the or kink in the optically thick lines, that might be a smoking gun. Perhaps I don't know. I'm not sure.
Okay, so looking at the different, I guess, yeah, the different, uh, like optically thick, optically thin lines, and then saying using those to like train a model effectively.
Yeah.
Yeah, that sounds really interesting. That's something I'll look into. Thank you very much.
Hi, thanks for your talk. Just a very quick question on your classifying a planet. I'm just wondering your model architecture. Are you planning like a XGBoost random forest as like a starting point? Or are you going into CNNs or what's your thoughts on that?
So my thoughts are I'd like to try and use CNNs if possible straight away. The amount of data we've managed to produce with the Latin hypercube sampling is on the order of like 500 plus kind of data points, and they would all be kind of images. So the most kind of natural approach to me, first of all, would be to try and apply a sort of a convolutional neural network. But if that's proves too computationally difficult, or then there's not enough data, then I might have to look at maybe um, different approaches to that. But I'd like to be able to sort of utilize the image-based nature. And from the stuff I've done in the past, I think that the CNNs are the best option for that. So fingers crossed that works.
Hi, Tom. Thank you very much for the talk. So I have a question related to the first one. So have you thought about including not just the kinematic data, but also data from, for example, other phases as dust, continuum, or scattered light in the machine learning algorithm?
Um, so at the stage I'm at, I'm currently like trying to get as much as I can to then put into. So it's I'm trying to effectively, I guess, yeah, come up with as many ways of getting as much data as I can in. So yeah, if there's, I guess, valid signals or like things that I think would influence, I guess, a prediction that I might be able to utilize, I would definitely consider using.